If you're prepping for a software engineering interview, we all know data structures and algorithms are kind of the ultimate boss battle. Welcome to today's explainer, where we are going to visually and methodically demystify standard sorting algorithms. By the time we're done, you're going to walk into that next interview with total confidence.
Let's start with a hard truth just to ease your anxiety right out of the gate. You are rarely, if ever, going to implement merge sort from scratch on the job. Day to day, we all just rely on built-in libraries, right? But here's the catch. For interviews, it's not about memorizing syntax. It is absolutely crucial to prove to your interviewer that you deeply understand the underlying mechanics of how data is actually organized and manipulated.
Okay, here is the roadmap for how we're going to get you interview ready. We'll cover 1. The interview reality, 2. Bubble sort and stability, 3. Merge sort versus quick sort, 4. Counting sort explained, 5. A real-life interview question, and finally, 6. Your action plan.
Section 1. The interview reality. Let's establish the foundational metrics by which all these algorithms are actually judged. Sorting is literally fundamental, but when you're sitting in that hot seat, just knowing the code isn't enough. You have to deeply understand these 4 core pillars: time complexity, space complexity, stability, and preferred usage. Your interviewer is going to test your ability to weigh trade-offs using exactly these 4 criteria.
Section 2. Bubble sort and stability. We're kicking things off with the absolute baseline algorithm practically everyone learns first.
Okay, so bubble sort has a time complexity of big O of n squared and a space complexity of big O of 1. Now, even though that time complexity is notoriously terrible, like seriously, never ever use this in production software, it actually has one super important redeeming quality. It is a stable sort.
So what does stability actually mean? Well, a stable sort is simply an algorithm where equal elements keep their relative input order in the final sorted output. Honestly, the only real-world reason you need to know bubble sort for a modern interview is just to beautifully explain this exact concept. It's the perfect, simple conceptual tool to prove you understand relative input order.
Section 3. Merge sort versus quick sort. Let's step up to the real heavyweights, the algorithms that actually power modern software. This is the classic showdown you've got to know. Merge sort runs in big O of n log n time and big O of n space, plus it's stable. It divides, sorts, and merges. Quick sort, on the other hand, gives you big O of n log n average time, but, and this is a big but, it carries a worst case of big O of n squared. However, it absolutely wins on memory, taking up way less space at big O of log n. The major trade-off here? Quick sort is not stable.
Now, theory is great, but let me explain this again using a real-life example, because this is exactly what interviewers love to see. To really lock this in, let's look at how Java handles this exact trade-off under the hood with its built-in sort functions.
This brilliantly illustrates our point. Java actually uses both, depending on the context. When you sort Java objects, it uses a variation of merge sort called timsort because stability really matters there. You want to preserve the original order of those complex items. But when Java sorts simple primitives, stability doesn't matter at all, so it automatically switches to quick sort for pure, unadulterated speed.
Section 4. Counting sort explained. Now we're going to look at a highly specialized algorithm that totally breaks the standard rules of time complexity.
You know how most standard comparison sorts max out at n log n speed? Well, counting sort operates in big O of n plus k time and big O of k space. It basically bypasses that whole n log n bottleneck. But there is a catch. It can only do this under one incredibly strict condition. The range of input values, which we represent as k, must be known in advance, and it's got to be small.
If the constraints are that rigid, you're probably wondering, when would I ever actually use this? Well, let's explain this again using a real-life example question.
The perfect real-life example and a super common interview trick is using counting sort to sort characters. Think about it. The alphabet is a perfectly known fixed range of just 26 lowercase letters. If an interviewer asks you to sort a massive string of text, please don't use a heavy n log n sort. Use counting sort because your k value is just 26, making it blindingly fast.
Section 5. Real-life interview question. We've covered the core theory, so let's put it into practice with a problem you might literally face tomorrow. Imagine you're in the interview, and they hand you this exact prompt. Sort an array of zeros, ones, and twos in big O of n time without any extra space. Right away, your mind needs to jump away from standard merge or quick sorts.
They want big O of n time and 0 extra space. That means they are fishing for one very specific trick.
This specific problem requires a famous computer science trick known as the Dutch national flag algorithm. It's this incredibly elegant categorization solution designed exactly for these strict constraints. To solve this in big O of n time without extra space, you totally ditch the traditional sorting loop. Instead, you initialize 3 distinct pointers, low, mid, and high. You just manipulate these 3 pointers across the array in a single pass, neatly shuffling the 0s to the front, the 1s to the middle, and the 2s to the back. It is a highly specific, brilliant little piece of array manipulation.
Section 6. Final Action Plan. We've covered a massive amount of ground today, from time complexities to Java's internal logic. Let's synthesize this into a rock-solid study plan.
Here is exactly what you need to take away from this explainer. First, know the merge sort implementation cold. You got to be able to divide and merge an array in your sleep. Second, know quicksort conceptually, specifically that it lacks stability. And third, know exactly when to pull out counting sort, like when you have a known tiny range such as an alphabet. Focus your practice heavily on these 3 deliverables.
The concepts are clear, the complexities are demystified, and the real-world applications are laid out right in front of you. So, as you head into your next big interview, the real question is, are you just going to rely on the built-in library, or will you be the candidate who actually knows what's happening under the hood when they ask why?